In this lecture, we're going to study the rules on reporting significant numbers or digits in measurements and calculations. In other words, how to be smarter than your calculator. Does anyone have any idea how many cells are in the human body? What's that you say? 40 trillion and 8? I'm relieved someone thought that was funny. What's funny about 40 trillion and 8 cells in the human body? The humor has everything to do with the last digit, the number 8. Any non-zero number in the last position implies that somebody counted that number. And yet no one has ever counted the number of cells in the human body. How long would it take to count 40 trillion cells in our body? It would take you more than a lifetime. And even if you tried to do that, the number of cells in the human body continuously changes. We're constantly losing cells, making more cells, and so even if you could make such a count, your count would be meaningless. But of course, you'd be dead anyway. The important thing to remember is that we use zeros as placeholders when we have no clue as to the actual value. 40 trillion is an estimate of the number of cells in the human body. The 8 implies counting. We should not have included that 8 on the end. By including that 8 on the end, we created a joke out of the answer. This leads us to the theory of significant digits. Only numbers in which we have some confidence in their actual value should be reported. When we have no confidence in the values of the numbers, we should use zeros as placeholders instead. The 8 at the end of 40 trillion should have been 0. We should have said, for example, that the standard reference adult human body weighing 154 pounds or 70 kilograms contains about 40 trillion cells. Notice that we are presenting only the first 2 digits as significant. Our reporting of the number of cells in the body must be an estimate, and we have confidence only in the value of the first 2 digits. The trailing 12 zeros represent placeholders. They are not significant. We do need them, however, because if we did not include them, we'd be saying that the adult standard reference male body has 40 cells in it, which would be ridiculous. We have a shorthand way in science of writing very large and very small numbers to indicate exactly how many digits are significant. This shorthand notation is called scientific notation. For example, we can convert the number 40 trillion to 4 times 10 to the 13th power. 10 to the 13th power is 10 times 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 10, which equals 10 trillion. Then we multiply 10 trillion by 4. And what we end up with is 4 followed by 13 zeros, or 40 trillion. Scientific notation is broken down into coefficients and powers of 10. The coefficient is the number in front of the power of 10. The coefficient must be at least 1, but less than 10. 4 is at least 1, but less than 10. The coefficient also tells us how many digits are significant. The fact there are 2 digits in the coefficient tells us that only those 2 digits are significant. In other words, only one of the zeros in 40 trillion is considered significant. All the remaining zeros are placeholders. Scientific notation gives us a shorthand way of writing very large and very small numbers to eliminate the ambiguity of whether any zeros are significant. We tend to go numb when confronted with numbers. The theory of significant digits is a means whereby we can think more critically about the numbers we report, as well as the numbers that others report to us. Let's say you go to the ballpark and they announce in the 7th inning that tonight's official paid attendance is 38,428. How many significant digits do we have here? We have 5 significant digits. All digits are considered significant because the paid attendance is a counted value. Now let's write our attendance in scientific notation, indicating the number of digits that are significant. How can you write 38,428 in scientific notation? Remember, the coefficient must be at least 1 but less than 10. If we write 3.8428 times 10 to the 4th, that's the same as 38,428. The coefficient, 3.8428, is at least 1 but less than 10. 10 to the 4th power means you move the decimal point 4 places to the right. By converting a number to scientific notation, we can indicate the number of significant digits, and we can write very large and very small numbers ending in place-holding zeros in a more compact form. Suppose you work at a ballpark and you estimate the crowd to be about 38,000 people. Note that I've highlighted the first 2 digits in red to indicate those are the only digits that we have any confidence in, which means that the trailing 3 zeros are mere placeholders. If they weren't there, we'd be saying there are 38 people in the stadium. Estimating 38,000 people in attendance with only the first 2 digits significant means that the actual attendance will be somewhere between 37,500 and 38,500 fans. If we convert our estimate to scientific notation, we would write 3.8 times 10 to the 4th power. The 2 digits in the coefficient, 3.8, tells us there's only 2 significant digits. The 10 to the 4th power tells us to move the decimal place to the right 4 places if we want to write our estimate in traditional form. What would we write if the paid attendance were reported as 38,000 exactly? Because this is a counted value, all the zeros are significant, and we would write 3.8000 times 10 to the 4th. Let's say we measure this line using 4 different rulers. Using the first ruler, we measure the line at 8 centimeters. The second ruler measures the line at 8.2 centimeters. The third ruler measures the line at 8.24 centimeters. And our fourth ruler measures the line at 8.244 centimeters. Which of these measured values gives us the most detail? It's the fourth measurement, 8.244 centimeters. We were able to extract more detail with our fourth ruler because it was divided into more gradations. The level of detail in a measurement will depend in part upon the quality of our instrument. Notice there are two rulers here. Both rulers are marked in millimeters. However, the top ruler is marked in 1 millimeter increments, whereas the bottom ruler is marked only in 10 millimeter increments. Because there's more gradations in the top ruler, we can get more detail and significant digits out of a measurement with the top ruler than with the bottom ruler. The level of detail of a measurement also depends upon the conditions under which we attempt to make our measurement, including the skill of the individual doing the measuring. Let's say we're trying to measure the height of Elvis in concert. Elvis is up there, gyrating his hips, huffing and puffing, and making it difficult for us to measure his height. If we attempt to measure Elvis in concert, and we report his height as 1.834576 meters, we're doing the equivalent of passing counterfeit money. There's no way we could measure the height of a moving individual to that level of detail. We could not measure a person's height to that level of detail in any meaningful way, even if they were standing still. A person's height continuously changes. When we breathe in, we get a little taller. When we breathe out, we get a little shorter. If you drink a glass of water, you get a little taller. If you're dehydrated, you get a bit shorter, and so forth. At the ballpark, they don't report the height of the players to that level of significant digits because it would be meaningless. Probably the best we could do in measuring the height of a person who won't stand still is 2 significant digits. Let's use these 2 rulers to measure the length of a line. Notice that the top ruler is divided into 10 millimeter increments. So we can count 10, 20, 30, 40. The line ends before it reaches 50 millimeters. So the line is somewhere between 40 and 50 millimeters in length. We're allowed to estimate one place when we do a measurement. So we count the first place as 1, 2, 3, 4, and now we estimate the second place. It looks like this line is just a little past halfway between 40 and 50 millimeters. So we estimate the second digit is 6 and report the line's length as 46 millimeters. The first digit is a counted value. The second digit is an estimated value. Someone else may use the same ruler to measure the same line and conclude it's 45 millimeters. Somebody else may say 47 millimeters. In other words, there's some uncertainty about that second digit, but we have no uncertainty about the first digit because it was counted. If we report a third digit, we would simply be pulling a rabbit out of our hat. We have no way of knowing what a third digit would be, and so a third digit should not be reported. Only one estimated place should be reported. Now let's measure the same line with the second ruler, the one that has the finer gradations. Now we can count individual millimeters. 10, 20, 30, 40, 41, 42, 43, 44, 45 millimeters, 46 millimeters. It looks like the line ends between 46 and 47 millimeters. I'm allowed to estimate one place, so I'm going to say 46.5 millimeters. Now, you may say 46.7, and someone else may say 46.4. There's some uncertainty about that third digit, but we should get reasonably close to agreement on the third digit. The first two digits should not be in doubt, because we counted them. Now, if we tried to extend our measurement to a fourth digit with this ruler, we'd be visiting Alice in Wonderland. In review, we could get two significant digits in our measurement legitimately out of the top ruler. But we can get three significant digits legitimately out of the second ruler because it has more gradations. In both cases, we estimated only the final digit. So the general rule in measurement is that the last and only the last reported digit can be an estimate. Now let's take our measured values and use them in calculations. When you crunch measured values, you can't have more significant digits in a calculated value than you had in the least of the measured values used in the calculation. Let's do some examples. Here's a rectangle. We measure the height of the rectangle at 2.0 units. We measure the width of the rectangle at 3.0 units. We get out our pencil to calculate the area of the rectangle. And what you get is that the area of the rectangle is 6.00 square units. Next, we get out our handy-dandy calculator and do the same calculation, multiplying 2.0 times 3.0, and our calculator spits back at us the naked number 6. What should we write down as the answer? A lonely 6 or 6.00? Neither. You should write 6.0. Why? Because we measured the size of the rectangle to only two significant digits. So we can report only two significant digits in our calculated value. If we report only one significant digit, we are losing information that we can legitimately report. When we report a single digit, we are saying the actual area of the rectangle is between 5.5 and 6.5. When we report two significant digits, we are saying the actual area of the rectangle is between 5.95 and 6.05, a far narrower range of potential values. Let's try another problem. What is the concentration of a solution that has 4.0 grams of solute in 0.30 liters of solution? Concentration here means grams of solute per liter of solution. Again, let's get out our calculator and divide 4.0 grams by 0.30 liters of solution. And our calculator spits back at us 13.3333333333333333. So what should we write down? If we try to write down what the calculator is spitting back at us, we would spend the rest of our lives writing threes. We've got more important things to do than spending our lives writing threes. But there is yet another reason for us to stop the insanity. It has to do with the significant digits in our measured values. What should we report as the concentration of this solution? 13 grams per liter. You can ignore all the threes to the right of the decimal place, because each of our measured values had only 2 significant digits. You say, but wasn't the solution measured to 3 significant digits? No, it wasn't, because leading zeros are not significant. The 0 before the decimal is a convention to prevent the decimal from being lost or interpreted as a period. Even if the leading 0 were significant, we still should have only 2 digits in our answer, because the measured value with the fewest significant digits determines the number of digits in a calculated value. The trailing zeros are significant in both measured values. There's no reason for the trailing zeros to be there unless they're significant. They're not needed as placeholders. So when we do the math, because our measured values were limited to 2 significant digits, all we should report as our answer is 2 significant digits. Those are the only digits we have any confidence in. Don't let your calculator deceive you. Here's another rectangle. But let's say we have 2 different people using different rulers measuring the sides of the rectangle. One person reports the height as 3.67 centimeters. The other person reports the width at 4.321 centimeters. Let's calculate the area of the rectangle. We get out our handy-dandy calculator and multiply 3.67 times 4.321, and our calculator spits back at us 15.85807 square centimeters. What should we report as our answer? $15.9 square centimeters. 3 significant digits. Why? Because the measured value with the fewest significant digits determines the number of significant digits in a calculated value. The measure of the height of the rectangle is 3 significant digits and limits the number of digits we should report in our calculated value. Note in the calculated value the 4th digit was 5. Because the 4th digit was 5, we can round up the last digit we retain. So if the 4th digit were 5, or 6, or 7, or 8, or 9, we could round up the preceding digit. If, however, the 4th digit were 4 or less, then we would simply drop it. What is the concentration of a 2.00 liter solution that contains 8.00 grams of solute per liter? Once again, we get out our handy-dandy calculator and do the math, and our calculator spits back at us a lonely 4 grams per liter. So what should we report as our answer? 4.00 grams per liter. Our measured values are reported to 3 significant digits. The zeros that are there are not placeholders. The fact that they are there tells us they're significant. And so we should retain their significance in the calculated value. In humdrum everyday life, when you're mixing a margarita, you'll probably just say 4 grams per liter. But in contexts where a high level of detail is important, you should report all the significant digits. So far, we've been looking at the rules regarding significant digits in multiplication and division. When we do multiplication and division, a calculated value should not have more significant digits than the measured value with the fewest significant digits. The rules for addition and subtraction are slightly different, however. In addition and subtraction, a calculated value should not have more significant digits than the measured value with the fewest significant digits to the right of the decimal. Let's look at an example. Suppose we have 10.32 pounds of sugar, and somebody brings us 4.4 pounds of sugar to add to our 10.32 pounds of sugar. We add these numbers together and get 14.72 pounds of sugar. What should we report as our new quantity of sugar? 14.72 pounds? No, we should report 14.7 pounds. Why? Because the measured value with the fewest significant digits to the right of the decimal determines how many digits to the right of the decimal we include in our answer. The 4.4 pounds contains fewer significant digits than the 10.32 pounds. We do not know the value of the digit that follows 4.4. It could be 1, it could be 4, it could be 7, it could be 0. When we did the math, the assumption was that it was 0, but that's an assumption. So the second digit to the right of the decimal in our answer is really a guess. Because it's less than 5, we simply drop it and report our answer as 14.7 pounds. Let's say we have 488.66 meters of rope, and someone reports that they removed 8 meters from the length of that rope. We calculate what's left as 480.66 meters. What should we report as the length of the remaining rope? 481 meters. Why? Because the person who removed 8 meters of rope did not report any digits to the right of the decimal, which means we have no idea what those values are. They could each be 0, they could each be 1, or the first digit could be 0 and the other could be 5. We have no clue whatsoever since they weren't reported, which means we really have no confidence in those 2 digits to the right of the decimal in our calculated value. So what we'll do is we'll round up, since the digit immediately to the right of the decimal point is greater than 5. We report our remaining rope as 481 meters. Let's say we have 12.5 meters of gold thread made of real gold, and someone reports that they have removed 3.5 meters of thread from the longer strand of thread. We put the numbers in our calculator, and our calculator reports back a naked 9 meters of gold thread remaining. What should we report as the amount of thread remaining? 9.0 meters. Both measured values included one digit to the right of the decimal. Even though our calculator dropped that digit because it was 0, we should include it in our reported final value. It is significant. If we report a naked 9, we are suggesting the actual remaining gold thread is between 8.5 and 9.5 meters, when in reality we can say the remaining thread is between 8.95 and 9.04 meters. These rules regarding significant figures and calculations apply only to estimated or measured values. In other words, values in which there is some uncertainty. They do not apply to counted numbers or defined relations. An example of a defined relation is 1 gram equals 1,000 milligrams, or 12 inches equals 1 foot. These are true by definition, not by measurement.